Is this username already taken? Is this link malicious? Have we seen this item before? A Bloom filter answers questions like these almost instantly, using barely any memory, and here is the strange, wonderful part. It can only give you two answers. Definitely not here. Or, probably here. It is never wrong when it says no. A no is always the truth. And it stores none of the items themselves, just a row of bits, flipping on. Let me show you exactly how, visually. One quick, honest note before we dig in. Everything in this video is free, no wall, no catch. This exact visual style is the whole idea behind my book, Algorithms and Data Structures, Visually Explained. 23 algorithms and data structures, each with a clean diagram and runnable Python. $24, link below. Totally optional. The full explainer is right here. Now, let us light up some bits. Here is the entire structure, and it is almost insultingly simple. 2 pieces. That is it. First, a bit array. Just a row of bits, think of them as light switches, and every single one starts at 0, all off. Here we have 16 of them. Second, a set of hash functions. In our example, 3 of them. Each hash function takes an item and spits out a position in that bit array, a number from 0 to 15. They are independent, so the same item usually lands on 3 different positions. And that is the whole thing. Notice what is missing. There is no list of items anywhere. We never store Apple, or a username, or a URL. We only ever store bits. That is the secret to why it is so tiny. So how do we add an item? Watch closely, because this is the core move. We take the item, let us add Apple. We run Apple through all 3 hash functions. Each one gives us a position. Say the 3 hashes land on 1, 5, and 11. So we go to the bit array and we set those 3 bits to 1. Bit 1, on. Bit 5, on. Bit 11, on. Apple is now in the filter, but notice, Apple itself is gone. We only kept 3 flipped bits. Now let us add a second item, banana. Run banana through the same 3 hash functions. Say it lands on 4, 5, and 9. Set those bits to 1. Bit 4, on. Bit 9, on. And bit 5? Bit 5 was already on, from Apple. So it just stays on. That is completely fine, bits get shared, and nobody records who set them. Adding is just, hash to k positions, set k bits. Always O of 1. Now the heart of it, the membership test. This is where people get Bloom filters wrong, so let us be exact. To ask if an item is in the filter, we run it through the very same hash functions. That gives us its positions, and we look at just those bits. The rule has 2 branches. Branch 1. If any of those bits is a 0, the answer is, definitely not here. Not, probably, definitely. Think about why. If the item had ever been added, adding it would have forced all of its bits to 1. So a single 0 is proof it was never added. This is a true negative, and it is rock solid. A Bloom filter never, ever gives a false no. Let us test grape. Grape hashes to 5, 8, and 11. Bit 5 is on. Bit 11 is on. But bit 8? Bit 8 is still 0. 1 0 is enough. Definitely not here, grape was never added, and the filter knows it for certain. Branch 2. If all of the item's bits are 1, the answer is, probably here. Not definitely, probably. Let us test Apple. Apple hashes to 1, 5, 11. All 3 are on. So, probably present. And in Apple's case that is true, we really did add it. But here is the catch, and it is the honest, beautiful flaw at the center of this whole idea. Probably really does mean probably. Sometimes the filter says, probably here, about an item that was never added. That is called a false positive. Watch it happen. Let us query cherry, an item we never added. Cherry hashes to 1, 4, and 9. Look at the array. Bit 1 is on, apple set it. Bit 4 is on, banana set it. Bit 9 is on, banana set it too. All three of cherry's bits are 1, purely by coincidence, set by other items. So the filter shrugs and says, probably here. But cherry was never added. That is a false positive. Now hold both facts together, because this is the exact promise of a Bloom filter. False positives, yes, possible. The filter can wrongly say, probably. False negatives, never, not ever. When it says no, it is always right. And the false positive rate is a dial you control. As the filter fills up and more bits flip on, coincidences get more likely, so false positives rise. To push them back down, you use a bigger bit array, or more hash functions. That is the fundamental trade, more memory buys you more accuracy. But no matter how you tune it, a no is always a true no. So why is this worth it? Because of what it costs, almost nothing. Add and query are both O of 1, just k hashes and k bit checks, no matter how many items you have added. And it stores 0 items, only bits. So it is a tiny fraction of the size of a real set or hash table holding the same data. There is a price for that. You cannot list what is inside a Bloom filter, the items simply are not there. And you cannot delete from a plain Bloom filter. Flipping a bit back to 0 might erase a bit that some other item still needs. Add and test only. And where does that trade pay off? Everywhere something wants to skip expensive work. Take databases, the storage engines behind Cassandra and Bigtable. Each one puts a Bloom filter in front of a chunk of data on disk. A lookup for a key that is definitely not there skips the disk read entirely. Web browsers and content networks check URLs against a Bloom filter of no malicious sites before doing a full lookup. Caches use one to avoid fetching things that were never stored. Spell checkers, and network routers, do the same. The pattern is always, let a tiny filter say a fast, certain, no, so the slow path only runs when the answer might be yes. Here it is in real, correct Python, the whole thing in a few lines. We keep a byte array of bits, all zeros to start, and a small helper that hashes an item to k positions. Add runs that helper and sets each of those bits to 1. And the membership test, returns true only if every one of the item's bits is a 1. If even a single bit is 0, all returns false immediately, definitely not present. So contains false is a certainty, the item was never added. Contains true is a maybe, probably added, but it could be a false positive. That is the entire Bloom filter, and it is exactly the semantics we just drew. Let us lock it in. A Bloom filter is a bit array, starting all zeros, plus k independent hash functions. No items are stored, only bits. To add an item, hash it to k positions and set those k bits to 1. To test an item, hash it to the same k positions and look. If any bit is 0, it is definitely not present, a no is always true, there are no false negatives. If all k bits are 1, it is probably present, which might be a false positive, set by other items. More bits and more hashes lower the false positive rate, trading memory for accuracy. You cannot list the contents, and you cannot delete from a plain 1. That is the whole structure, O of 1, and almost no memory. It is why databases and browsers use it to skip work they can prove is unnecessary. So that is the Bloom filter. A row of bits, a handful of hash functions, and one unbreakable promise. It can say, probably yes. But when it says no, it means it. Next, we leave data structures behind and watch a program do something that feels almost alive. Instead of being told the answer, it evolves one. Random mutations, crossover between candidates, survival of the fittest, generation after generation. Slowly a solution emerges from what looks like chaos. When brute force is hopeless, this is how you search anyway. That is where we go next. Genetic algorithms, visualized. And if you want the whole picture, 23 algorithms and data structures, each with a diagram and clean, runnable Python. My book, Algorithms and Data Structures, Visually Explained, is linked below. $24, totally optional. Subscribe, and I will see you in the next one.